Hello, and welcome back to Backer Breaks It Down. In this episode, we continue talking about tangents. This is part two, more on tangents. So, in our previous episode, we talked about how a tangent, where it meets the radius, is perpendicular, so we've got a right angle. And we also talked about the two tangent theorem that said if two tangents are drawn from the same external point, then they are congruent. So let's just build on our knowledge of tangents. So common tangents, basically we're talking about if you have two or more circles, if they have a common tangent, they have a line that's tangent to both of them. So a line is going to touch each one of the circles, is only one place on the circle. And it could be an internal tangent, which means it would be in between the circles, or it could be an external tangent, which means it wouldn't be in between the circles. So that's just a matter of vocabulary. So we're going to use something called the common tangent procedure to find the length of our external tangent. Okay. And the key here will be working with that theorem that says that when a line is tangent to a circle, it'll be perpendicular to the radius at that point. Okay, so in this problem here for circles Q and P, AB is a common tangent. And so where that common tangent is meeting each of our circles, their radii specifically, we are going to have these right angles. Okay. Notice that circle P has a radius of 8 centimeters and circle Q has a radius of 18 centimeters. And our goal is to find the length of AB. Okay. And so they offer us this procedure that we can use to figure this out. The first step says that we should draw the segment joining the centers. So that's easy. Okay. Through the center of the smaller circle, draw a line parallel to the common tangent. So I guess I'll just stick with my red. So I'm going to draw parallel to the common tangent. Okay. This line will intersect the radius of the larger circle to form a rectangle and a right triangle. Okay. So I am seeing, I'll just highlight this for you. So here's the rectangle. Right? And then directly below that is our right triangle. So what do I know about this right triangle? Well, I know that this leg here is x units long. Okay. I know that the segment going from Q to P, I do know how long that is, and so do you. Because remember, the radius of our larger circle is 18. The radius of our smaller circle is 8. So if you were to add 18 plus 8, that's going to give you 26. Okay. And then when it comes to this leg of our right triangle, we know what it is. Okay. Because we know the opposite sides of a rectangle are congruent. So this is 8, therefore this is 8. Are you seeing what I'm seeing? So that would mean that green identified segment there is 18 minus 8, making it 10. So I know one of the legs is 10. I know the hypotenuse is 26. And so the only thing I'm missing is the other leg. And so, yeah, Pythagorean theorem, yep, we're using it here as well, because I can say the leg squared plus the other leg squared is the hypotenuse squared, and then I can do my math. We get that x squared is 576, and then we're just going to take the square root of that. my calculator will let me. And I get 24. So that's like the length of the common tangent, right? So we just found a tangent length. I think it's only fitting that we talk about, since it is a line, a tangent is, how do you find the equation of a tangent? And so that's what our last problem is addressing. Now, we have, like, first semester in geometry, we found equations of lines. So like this is nothing new to us. We're just connecting it to tangents. So here we have a circle centered at C with the coordinates 4, 5. Line J is a tangent. Notice that the point of tangency is P. The coordinates are 8, 3. So ultimately, I want to find the equation of the tangent line. In order to do that, I need to know its slope, right? Well, like I don't have 2 points on that tangent line to work with, so I'm going to work with the radius, okay? So I'm going to find the slope of my radius. I'm going to use my slope formula to do that. So I'm going to have my slope is equal to y2 is 3 minus y1, and I'm going to divide that by x2 minus x1. So we have negative 2 over 4, so that's negative 1/2. So I know the slope of the radius is negative 1/2. I can use this to find the slope of the tangent, right? Because remember, the tangent is perpendicular to the radius, and perpendicular lines have slopes that are opposite reciprocals, right? So if the radius has a slope of negative 1/2, then my tangent line will have a slope of positive 2, because that's the opposite reciprocal. So now I'm ready to write an equation for my tangent line, and I can use my point slope form to do that, right? Since I'm writing the equation of the tangent line, I want to use a point on that. That's where point P comes in. So I'm going to use that and my slope to write my equation. So I'm going to have y minus y1 is 3 equals my slope, which is 2, times the quantity x minus x1, which is 8. And then it's just a matter of distributing on the right-hand side and then getting y all by itself. So if I add 3 to both sides, the equation of my tangent line is y equals 2x minus 13. So we're just using the fact that the tangent is perpendicular to the radius. That allows us to find the slope of our tangent line, and thus we can find the equation. And that's how Bakker breaks it down.